Okay, so here's the infamous ladder problem. A 25.9 kilogram person climbs up a 75.6 Newton uniform ladder. The upper end of the ladder rests on a frictionless wall. That means this one. The bottom of the ladder rests on the floor with a rough surface. The angle between the horizontal and the ladder is 48.8 degrees. The person wants to climb up the ladder a distance of 1.8 meters along the ladder from the ladder's foot. So one thing I want to mention before we move on to the question is this means there's friction. Okay, that's all it means, and that's why you have the coefficient of friction over here. Find the frictional force between the floor and the ladder when the person is 1.8 meters from the foot of the ladder. The acceleration of gravity is 9.8 meters per second squared. Answer in units of newtons. All right, let's write down what we know. So let's start with the length of the ladder, just by the text. So you have the mass of the person. I'm just going to call it M. Weight of the ladder, I'm going to use lowercase w, and then an L for the ladder. Don't forget, that's the weight of the ladder. The angle between the ladder and the horizontal, I'm going to call theta. The distance from the bottom to where the person is, I'm going to call d. You can call it whatever you want. And then the length of the ladder, I'm going to use capital L. And I know the coefficient of static friction. I can write it down. Just want to let you know we're not going to use it. And we have to find, well, we know the acceleration of gravity. And we need to find the frictional force, lowercase f. The ladder would slip to the left, therefore there's a force to the right. So right now what I did is I'm about to show you, I traced the ladder a few points, and I have the magnitude of the forces, not to scale. So here's my sketch. Pause it, you can copy it down. Let's start by the forces. So this is the force between the wall and the ladder. So I'm going to call it the force of the wall. I could call it normal force of the wall. I'm just going to call it the force of the wall, FW. This is is about the midpoint of the ladder. Because it is a uniform object, uniform ladder, that means its center of gravity is at the center. So that one I'm going to call the weight of the ladder. So there you go. This is where the kid was. So the kid is applying a force by means of his weight or her weight, whatever. So that's going to be mg. This is the frictional force. This is the one I want. So lowercase f. And this is the normal force between the floor and the ladder. Okay. So now, this is a problem obviously about torque. We got to see what forces are acting on the ladder in such a way that you will have torque. Now, first of all, these two forces are not trying to apply a torque because the pivot, the axis of rotation, would be here. Therefore, the distance here for both would be 0, so torque would be 0. That is, we have 3 different torques being applied on this system. And I'm going to call them torque 1, torque 2, and torque 3. Let's use blue for that. Okay, so what do we do? Well, this system is in equilibrium. That means the sum of the forces is equal to 0, net force is 0, and the net torque is 0. Both conditions for equilibrium have been met. Let's start by trying to get equations for these 3 torques. Let's start with torque 1. So the general equation for torque, as we know it, is simply torque is equal to the radial distance times the force times the sine of theta. So let's start with torque 1, right? What is torque 1? Well, what is the radial distance for torque 1? Well, the distance, the axis of rotation is here. The distance would be the length of the ladder. So let's begin building our equation. So torque 1 is going to be distance of ladder. We said L. The force is the force of the wall. Now, if, let's say, you could have someone push the ladder at this point, the ladder would then go like this, counterclockwise. So there's a force trying to rotate. So let's call it force of the wall. And because this is theta, then I know this is also theta. All right. Now, I think most of us are going to be inclined to say just sine of theta. However, although that's going to be correct, I want you to think of torque in a different way now. I want you to think of what is the perpendicular component acting on the ladder. So the perpendicular component of this force acting on the ladder, because this force is not at 90 degrees. So if I were to break this force into components so that one of them is perpendicular, I would have it like this. Okay, so here's my 90-degree angle. The one thing you have to be mindful about is this force has to be your hypotenuse, has to be your resultant force, because you're decomposing this force. Okay, so then by geometry, I know that this is also theta. I meant to use purple. There you go. And this is the force perpendicular to the ladder. Now, if I use trigonometry, if this is theta, this is opposite. So this component would be force of the wall sine of theta. So then that means my force is going to be multiplied times the sine of theta. Because we know that torque is a cross product, right? So we have to be careful about orthogonal vectors. All right, there you go. Let's do the same thing for all of them. Because none of these forces, these three forces, are perpendicular. So I'm going to decompose these forces into components at once. Okay, let us start with this one, the weight of the ladder. So this is the perpendicular component. Here's my theta by geometry. So this side, or this force, is adjacent to theta. Therefore, the force I need to be thinking about in terms of torque is going to be weight of the ladder, because it's adjacent, cosine theta. It will be the same thing here. I have theta. This is the force perpendicular, so that'll be mg cosine theta. That tells me what is the force perpendicular to the ladder. So when I build my torque equations, I can just use those over there. Let me move this out of the way. Okay, so torque 2. Torque 2 is going to be here. Now the distance, because this is the center of gravity, or it's going to be half the ladder. If the ladder has a length of L, so half it, that distance would be L divided by 2. Then the force is the weight of the ladder. And then we said the perpendicular component would be the cosine component. For torque 3, we have this distance here. That distance, we called it D. It was 1.8 meters, the distance to the person, to the kid. So then it'll be D. And then the force is the weight of the kid, so mg. And then the perpendicular component had to do with the cosine, so cosine theta. Now, let's see as far as direction goes. This would cause a counterclockwise torque, so that would be positive. These two would cause a clockwise rotation, so these two are negative. So then I know when I apply the second condition for equilibrium, sum of the torques is equal to 0, which would be torque 1 minus torque 2 minus torque 3. Because of these signs. Now I can rearrange my equation, because I am trying to solve for the force of friction. And you'll see why or how we get the force of friction, because I know it's nowhere to be found here. All right. So with a little bit of algebra, I know that torque 1 is equal to torque 2 plus torque 3. I'm going to use my bottom portion of the page. So I note torque 1 is the length of the ladder times the force of the wall times the sine of theta. Torque 2 is half the length of the ladder times the weight of the ladder times the cosine of theta, plus distance d times the weight of the kid times the cosine of theta. Okay, there you go. Now let's sum the forces to see what we can do and how we can get force of friction involved. Let's start with the x direction. So for x direction, I only have the force of the wall and force of friction. I'm going to make the force of the wall positive just because I made this torque positive. I could make it negative and nothing would happen, okay? This is equal to 0 because system is in equilibrium. Now for the y direction, I'm going to have these three. I'm going to make the normal positive just because. Okay, so what can we use there? Because I'm trying to solve for force of friction, I can use this equation. Because these two sum to 0, I know they are equal and opposite. So I can just say force of the wall is equal to the force of friction. So I can rewrite this equation and substitute force of friction here. In all truth, guys, that's all the physics. From here, all we got to do is mathematics. So I need to solve for force here, right? Force of friction. So I'm going to divide both of these by length of the ladder and sine of theta. Okay, in all truth, this is enough for you to find the answer because you know all of these quantities. Length of ladder, the weight, the angle, length of ladder again, distance, mass. You know all those things. But of course, we want to make this a bit more elegant. So let's do just that. The first thing is I have cosine over sine. I know that's going to be cotangent or 1 over tangent. So let's rewrite it. Okay, so I decided to show the cosine over sine. So it's going to be 1 over tangent or cotangent. Desmos, I couldn't find the cotangent function there, so I'm just going to use 1 over tangent because I know most of my students use Desmos. But if you have the cotangent option for yours, you can substitute with this with cotangent. And then I'm just going to combine or simplify this one. We can get rid of the length of the ladder here, and then I'm going to factor out 1 over tangent. That's the equation, the one I was able to simplify. That'll give you the force of friction. Again, this one will also give you the force of friction, but this one is easier to work with. All I got to do is plug in your numbers, and that's it.